Let's derive the formulas for the mean and the standard deviation of a binomially distributed random variable. So to find the mean of the random variable x, so it should have a fixed number of trials, that's represented by n, and a fixed probability of success, that's represented by p. Now remember the other two conditions that are also necessary. I would want to believe that there are only two possible outcomes, so we have either a success or a failure. And I would also want to believe that each trial is independent of every other trial. So let's start by considering a simpler random variable. Let's call it y. So let's say y is distributed binomially. But it's extra simple. It has only one trial and a success probability of p. So it's easy to find the mean and the standard deviation for y. So with only one trial, you either have 0 successes or 1 success. So 0 and 1 are the two possible outcomes, 0 successes or 1 possible success on that one trial. So here's the formula for the expected value, or mu. I need to take every outcome times its probability. So this is not particularly hard. So the outcome 0 successes. So if our count of successes is 0, the likelihood of that is, that's the failure. The probability of failure is 1 minus p. So if we actually have our one success on that one trial, the success probability is p. So these are the only two possibilities, 0 successes or 1 success. That one success has a probability of p. The failure then has to be all of the rest of the probability. Its likelihood is 1 minus p. We've added these up. That's what the formula for expected value tells us to do. So 0 times anything makes 0. So here 1 times p makes p. That is the expected value for the random variable y. So to find the standard deviation, and notice there is an error here on this handout, this should be sigma squared. That represents the variance. We want to start by calculating the variance. So the variance of y, will take every outcome, subtract the mean, that's a deviation. We'll square that, and we'll weight each of those squared deviations by their probabilities and add them up. So there are two squared deviations that we need to consider. We're going to multiply by their probabilities. So here we go. The first possible number of successes is 0. The mean number of successes is p. So I need to take the 0 minus the p and square it and multiply by the probability of 0 successes. That probability was up here, 1 minus p. That's the probability of failure. So we could have 1 success. The average number of successes, the expected value is p. There's our deviation. We need to square that and multiply by the probability of that 1 success. That is p. So this is our expression for variance. So notice 0 minus p simply makes the opposite of p, but you can think of that as a negative 1 times p. And if we square that negative 1, we make a positive 1. So essentially this expression just becomes p squared. This expression is 1 minus p. There is the sum. Here is 1 minus p. That quantity is squared and then multiplied by p at the end. So I want to find the greatest common factor of this expression. There are two pieces. So here is one piece. All of these pieces are multiplied together. Here is the other piece. And they're separated by this addition sign. So notice each of these shares at most 1 p. So I'm going to factor out that p as the part of the greatest common factor. So understand then, from the first expression, I have taken out one of these p's, so I'm just going to take off that exponent. So I've put that second p out here in the greatest common factor. From this second expression, I've taken this p and put it in the greatest common factor, so it's gone. I've put it in front. Now notice these two expressions also share a 1 minus p. This one has a factor of 1 minus p once. This one has a factor of 1 minus p twice. So I can factor into the greatest common factor the quantity 1 minus p. So from the first expression, I have taken this 1 minus p and I have put it into the greatest common factor. Here it is. From the second expression, there are two 1 minus p quantities. I have put one of them in the greatest common factor, so I'll represent that by just taking away the exponent. So now look at what remains then. I have a p, there it is, plus the expression 1 minus p. There it is. So I have taken the greatest common factor, and what remains then I have put in parentheses here. So essentially we're just using the distributive property backwards. And I can simplify this expression. So I have p. This quantity remains 1 minus p. And of course p minus p gives me 0. So this final expression is just multiplying by 1, so I don't have to bother multiplying by 1. This expression represents the variance of y. So understand what we ultimately want are the mean and the variance and the standard deviation for the binomial random variable x, where x has n trials and a success probability of p. So what I have found are the mean for y, my simpler binomial random variable with only one trial. And I have also found down here the variance of y. So we're going to use these in order to build the mean and the variance and the standard deviation for x. So we're really interested in x, but notice that x is the same as n independent. N independent y's added together. So understand y has a value of 0 or 1. We either have 0 successes or 1 success. So x represents n trials. So notice if each of these y's is a success, x will take the value n. We would have n successes. So the number of successes for x is just determined by adding up individually how many of these y's happen to be successful or not. So notice this is a linear combination of n y's. And if we assume that these are all independent of one another, remember, for a binomial random variable, I need two possible outcomes, a success or failure. I need a fixed number of trials. Here I have n of them because I'm adding n of the y's together. I have to believe that my success probability is always the same. It is. It's always p. And I have to believe that all of my trials are independent of one another. That's why this is so important. So understand then, the mean of x can be found just by adding together the means of all of those n y's. So every one of these y's has a mean, as we found up here, of p. So literally every one of these means is replaced with a p. How many y's did I have to add together to accomplish this? I had to add n of these y's together. So there are n p's right here. So the simplest way to write this is n times p. And that is the expected value, or the mean, for the binomially distributed random variable x. The mean is n times p. So to find the variance for my binomial random variable x, notice I'm thinking about x as a combination of n of these simpler random variables y all added together. But if they're all independent, I can add their variances. So the variance for the first y, the variance for the second y, all the way to the variance of the nth y, but I know what all of those variances are. They're all represented by p times 1 minus p. P times 1 minus p for the first random variable y. P times 1 minus p for the second one, all the way up to the nth one. So again, notice this happens n times because I am adding n of the y's together, they're all independent, in order to make my x. So that means that the variance for my x is literally just n of these p times 1 minus b expressions. That is the expression then for the variance of the binomially distributed random variable x. So to find the standard deviation, I can just take the square root of that expression. So that would be the square root of n times p times 1 minus p. And that ultimately was our goal. So when x is distributed binomially with n trials and a success probability of p, and we have our 4 conditions satisfied, then the mean of x is represented by n times p. The variance of x is represented by n times p times 1 minus p. So the standard deviation is the square root of n times p times 1 minus p.